Most of us understand Newton's first law at this point, that an object in motion stays in motion unless acted on by a force. But there's another thing to consider about this. What does it mean to stay in motion? It doesn't just mean to keep moving. It means to keep moving at the velocity you have in the direction you were going. If you want to have somebody move in a different direction, you got to apply that outside force. And a really good example of this is turning. What if we wanted our person here, instead of moving straight, we wanted them to round a corner like that? I've drawn this new path as a circle, and I did that because that's the easiest type of cornering motion to understand. So we'll treat this as circular motion. So if the law of inertia, Newton's first law, says that our person should continue in this direction, we have to ask ourselves, what direction would a force have to be to get us to start moving in a circle? Well, notice that my white line has started to go below my yellow line. So here it's probably a downward force. Something like that. As we continue though, now we're going a little more to the left than we'd expect if we were going to go in a straight line. So the force is turning a little more to the left. If we're going to go in a straight line here, we'd be shooting down the board, but we're turning to the left of that. And I think you can see that as I go around, the force needed to keep me moving in this circular path is an inward force. We call this type of force the centripetal force. And that's just Greek for center seeking. So what I'm going to do now is I'm going to run around a corner, and you're going to see that this inward force is absolutely necessary. I'm going to do it in a situation where I don't have enough of it, where there's not an inward force to help me turn, and I want you to predict what's going to happen. So the coefficient of friction between my shoes and the tile floor, it's pretty high, and as fast as I can run, the frictional force appears to still be enough to hold me in a turn as I'm going. So I taped some cardboard to my feet in order to decrease friction, and we'll see what happens. We'll pay special attention to the direction I go in as I try to round the corner. So I think it was pretty clear what happened when I didn't have enough of this inward or centripetal force. I kept flying outward. And sometimes people think that there's an outward force that's pulling them out as they try to round a corner. And they even make up a name for this. Sometimes they call it the centrifugal force, the center fleeing force. But that's not really what's going on. If I want to make this white curve, I have to consistently have this inward force. When the inward force is not enough, well, what am I? I'm an object in motion, and I want to stay in motion. So let's say I'm going fast enough here that I no longer can provide enough inward force to turn me. What do? And that's what you saw in the hallway as I went flying outward. From my perspective, it really felt like I was being pulled outward. But I think from the angle you guys were at, you could see that I just failed to make the turn. And it was my inertia, my momentum, the fact I was an object in motion, that's what kept me going. There was no outside force. What we need to do next is we need to study what these inward forces are. And I think you saw from this video that the inward force for me was friction. These inward forces aren't some magical new force. They're always going to be something we've studied before. So the big idea of these centripetal forces is that they're
not anything new. They're all forces we already know. They just point in a particular direction. I'm going to start by talking about tension forces. So here's the force picture free body diagram for me swinging one of the Angry Bird stuffed animals along on a string. So as you can see, there's an inward directed tension force, and it's the tension in the string. The bird will continue to move in a circle until that tension force goes away, like the string breaking or me letting go. This picture here on the lower right, this represents me on my way to school, skidding out on an icy morning when we didn't have a delay. You could see my car is proceeding on North Main Street. I was trying to turn onto Wadsworth, and that's always a pretty slippery place. And I wanted to follow this purple path and have an inward frictional force. But the frictional force was not enough, so I was an object in motion and I stayed in motion. I didn't actually leave the road, but I started to drift outward. Again, that's not an outward pull, that's just me following my inertia. So here's another look at that car moving in a circular track. You can see its velocity is always tangent to the circle. And the inward force is caused by friction, like before. This tries to make the point, though, that if it's no longer going in the direction it was, if it's changing its velocity, there must be an acceleration. So that acceleration is something we're going to have to look at. Just wanted to show a couple other forces that can cause things to move in a circle. This is a beam of electrons moving through hydrogen gas, and you can see it's in a circle. The electrons are being tugged on individually by a magnetic force. Finally, gravity can cause circular motion. Here's an actual picture of the moon orbiting the Earth, and the inward force is supplied by gravity. This is a good problem for trying to see how we can mathematically understand circular motion. So I have the Angry Bird. It's swinging around on a string like you saw before. I have the length of the string, and I have the speed. Let's try to figure out about forces on it. Here's our force picture, or free body diagram, and we can see we have an inward direction tension force. And that tension force is actually spinning as we go around the circle. This makes x and y axes hard to set. Do you set them so they are tangent and radial to the circle in one location? Because then they're not right for the other location. Y is no longer pointing into the circle over here. It's no longer pointing tangent over here. So usually for circular motion, we actually make up two new axes, t and r, that actually spin with the object. Don't stress about that too much. The r-axis is kind of like the x-axis. The t-axis is kind of like the y-axis. So let's finish the problem. As you can see, we have to do a sigma f equation. If you're in uniform circular motion, that means that you have no acceleration along the t-axis, or in other words, tangent to the circle. And this equation, which we will derive in lab in some classes, describes your acceleration inward. The inward acceleration we know has to be there. So you just do a sigma f equation. In our case, our only radial force is tension. The a is this new acceleration, so we can plug in and we can solve for how much tension has to be. Let's look at another problem like this. Here's another nice problem using a spring force, which we haven't looked at in a while. It looks like a complicated problem, but it's actually just as simple as the other. It says you have a hockey puck on a spring, you spin it. The faster you spin it, you expect the spring to stretch more and more. And they want to know what the spring constant is when you're going a certain speed and the spring is stretched a certain amount. So again, this is just a sigma f equals ma problem, and our only radial force is the spring. So I've replaced a with this new v squared over r equation. The spring force I replaced with the equation for spring force. And you just plug in and you end up getting k. Let's look at a couple more problems where there's more than one force acting. So here's an example from lab you may do in class. We have a weight hanging from a string, and the weight can move up and down along what's essentially a circular path. Now you know the tension force is going to be changing its direction depending where it is. Gravity, of course, will always point down. So when you've got more than one force, sometimes your sigma F equation is only true at one location. So this one's true for when the weight is at the bottom. And we have sigma F equals ma. We have Ft minus Fg equals ma. We plug in mg for Ft. I didn't do it here, but you could plug in that new v squared over r for a, and then you could relate speed to tension as you move along the circle. So it's just a 2D force problem. If you have more than one force, it's just like having more than one force in 2D. I thought we would finish with a couple of fun problems. Have you ever wondered about the Earth spinning and how that affects your motion? Have you ever wondered what would happen if the Earth sped up? What would happen to you? Well, you could solve that now pretty easily using our new circular motion acceleration. What I'm doing here is I'm following Paul Hewitt's convention, and I'm representing the Earth spinning faster by making v bigger and bigger. You could see our sum of force equation, free body diagram, shows an upward normal force and a downward force of gravity, and that's what sigma F turns into. So as you start to go faster and faster, this side of the equation gets bigger, so this side must get bigger too. That means the normal force must drop. At some point, the normal force can't drop anymore. This would be you moving around the Earth with the Earth barely having to push you up. What would happen if you go faster? Let's look. I wanted to invite a friend here. So I've got Abraham Lincoln. We're going to bring him home to Illinois there. Hello, Lincoln. And we're going to give the Earth a little bit of a spin. So the Earth rotates, and not surprisingly, Lincoln stays on it because the Earth's rotation is at a moderate enough pace and the Earth is so big that it doesn't overcome the force of gravity. In this case, it doesn't overcome the force of the masking tape, and it stays put. But if the Earth were to spin faster and faster, he would go flying. And I want to see if I can cause that to happen. So we'll give the Earth a good spin. And sure enough, he goes flying outward. So that outward motion in a straight line that would occur if Earth spun fast enough to fling us off it, that is the reason that we feel like we weigh slightly less than we actually do. Obviously in the video, I used the stickiness of the tape, the adhesion force, to stand in for gravity. Let's look at one other, which is a fairly famous demonstration and maybe something you've wondered about in the past. A lot of people have trouble with remembering the direction of the force of something moving in circular motion. The rule is pretty simple. If it's moving in a circle, there's always an inward net force along the radial axis. But even if we learn that rule, we practice that rule, people still occasionally think there's an outward force, which is sometimes called the centrifugal force. It's not really there, but let me do a demonstration that would almost make you think otherwise. Got a bucket. Got some water. This is a pretty full bucket. Tip a little bit out. But despite that, I'm willing to swing it in a circle over my head. And obviously I did not get wet. So what direction were the forces on me here? Believe it or not, inward. The most obvious force, of course, would be the force of gravity on the water. But the other force comes from the fact that this water is moving in a circle. And it would prefer to be moving in a straight line path. It's an object in motion. It wants to stay in motion. And what that means is,
it's getting pressed on by the bottom of the bucket. A normal force is being put on the water, and that's holding it in the circle. These are downward forces, so it almost looks like I should have gotten wet there. Why didn't I? Because we have to remember the direction that the water would travel if the bucket were to suddenly vanish. It's an object in motion and wants to keep going that way. Because gravity exists, it's going to move in a parabola, kind of like that marker. And it's going to follow this kind of path. Well, notice that that path is outside the circle of where I'm swinging the bucket. So by the time the water would get to here, the bucket's already in this place and it's trapping it. If it was going to be here, the bucket has already swung it into a different location. So it's not any force that's keeping the water up. There's no outward force. It's just that because the water is moving so fast to the side, it can't fall directly on me. And by the time it starts to fall, the bucket is already turned. So it sounds convincing when you look at the forces, but when you're swinging the bucket of water over your head, you really do feel like the water's being held up by something. Nothing's holding it up. It's just its inertia.
So I wanted to talk about different paths that the bucket might follow. This discussion comes from one Paul Hewitt had in his books a few years back, and I think it's a very valuable discussion. We could see the green path that the water in my bucket would have taken if the bucket suddenly vaporized. And that is clearly outside the orange path the bucket took. So the water stays in the bucket. What if I started to slow down? Well, this blue path is a little narrower, and we know that that's what happens when you throw a projectile slower. That's what the water would do too. This black path, notice it parallels the path of the bucket at first. In this area, the two are basically following the same path, and that's the minimum safe speed that you can go so that the water doesn't fall out. If you went slower, it would fall inside the path of the bucket and you'd get wet. So let's talk about why the water stayed in the bucket. Really the big deal for physics is why the water went in a circle. We see that the sum of force along the radial axis is equal to ma, or mv squared over r in this case, since it's moving in a circle. And our force picture free body diagram tells us that that's gravity plus the normal force that's holding it in a circle. Let's look at that for various speeds, and we'll use Paul Hewitt's formulation of making letters bigger when they correspond to bigger values in order to see that. So we can see here that the green path, the farthest outward one, it was moving very fast. That's why, according to Professor Hewitt, I drew the big V. And since the force of gravity is fixed in its size, the only way to make the left side of the equation big to match the right side would be to have a large normal force. The bucket's having to push the water pretty hard. In the case of the blue path, we know from its shape that it's slowed down. So that's why I drew a smaller V. And the only way to decrease the left side of that equation would be to make the normal force decrease. So if we talk about the black path, how could we go slower? Well, if the right side of the equation, mv squared over r, is going to be smaller because we're slower, so does the left side have to be smaller. The only thing we could do is decrease down to the point where there's no normal force. That's the slowest you can go. Any slower, the force of gravity is going to be bigger, and that's when you're going to get wet. So we can solve, according to Professor Hewitt, for the black curve, we could say the force of gravity equals mv squared over r. When we solve that around, we see that g must be v squared over r, and v is the square root of rg. That's the slowest you can go if you don't want to fall off. So I hope this introduction to circular motion has been useful to you. We will practice a lot more problems in class.